This is Cosmographia, the Randall Carlson podcast. And welcome, ladies and gentlemen. This is a special episode of the Cosmographia podcast with Randall Carlson. This is for Asteroid Day, right, Randall? The presentation you have for Asteroid Day?
Yes. Yeah, I would say yes. But the one thing that I was a little confused about is that aren't all the episodes special? Or is it just this one is special? I was thinking all along that they were all special, but this one then could be considered extra special.
Right. It's special relative to the other episodes. Yeah.
Well, I thought what we would do is we would just introduce some ideas that are going to be very much expanded upon in the upcoming episodes. And it would be appropriate to release it on or about June 30th, which, as you said, Asteroid Day. So why is June 30th chosen as Asteroid Day? Brad, would you like to comment on that?
Well, it's the anniversary of the Tunguska event over central Russia, in 1908.
In 1908.
So they decided to make this an annual event to try to raise awareness of there being more and more in our space around us that we're aware of. So they need to make the people aware of that so they can get funding and start detecting these things and maybe protecting the planet from them.
So let's a little more background on Asteroid Day. Who came up with the idea and who actually started it? It wasn't the B12 Foundation, was it?
It may be some of the prior astronauts. I don't know that 100%.
I think it was. Perhaps, Kyle, you would look up Asteroid Day.
On it.
You're on it.
One of them is Rusty Schweikert and Ed Lieu.
That makes sense.
They're part of the B612 Foundation. They've got a Sentinel mission. They're mapping the inner solar system of all the orbiting objects. They're trying to get a telescope in space to better detect the objects out there. But it's just in the past 2 years that it's been recognized by the UN as an international event or an international day. So
this is really cool. Asteroid Day was co-founded in 2014 by Dr. Brian May, astrophysicist and lead guitarist of Queen.
Queen, right.
Together with Danica Remy, president of B612 Foundation.
I knew there was the B612 connection.
Rusty Schweikert,
Brad just mentioned
Apollo 9 astronaut and filmmaker Grig Richters, I guess. So yeah.
So that's
rock and roll and asteroids.
Yeah, I forgot
rock
about
and roll
Brian
and
May.
asteroids. I've always thought that was a good fit. So 1908, June 30th, early in the morning. Would have been around 7:30 local time, give or take a few minutes. And what happened? Well, it depends on, I guess, your vantage point. Interestingly, it appears that there's nobody who is documented to have died immediately from the event. There are stories that probably some of the older citizens that were the Tungusi people that were within the vicinity may have suffered to the extent where their demise was hastened. Because there were people that were literally, even though they weren't within the blast zone itself, the shock wave moving out was enough that even 30 and 40 miles away, people were blown off their feet. Some cases, people blown 20 and 30 feet through the air to smash against a tree or whatever. So, there was undoubtedly sustained injuries, but there were no documented deaths of any individuals directly as the result of the explosion. Now, there was a herd of reindeer, as we talked about, that apparently was incinerated because they were grazing very near the epicenter. Let's pull up a.
And I know you'll get into this, but I mean, just to be clear with it up front, it is June 30th annually because that is the annual return of one of the torrid stream meteor showers.
Yes, and we certainly should talk about that too, because this ties in with everything we've been talking about up to this point regarding the Younger Dryas impact and the possible connection between the Younger Dryas impact or impacts and the torrid meteor system, the family of torrid meteor streams that all seem to be interconnected and to be the progeny of perhaps one really big comet that came into the inner solar system sometime between 20 and 30,000 years ago. I would say actually more like 25 to 30,000 years ago, because I have a strong suspicion that if this bears out, that there was in fact, and it's appearing pretty incontrovertible at this point, a very large comet that came into the solar system. I would be looking for some sort of a climatic or biotic signature of that event. And what we do in fact find is that generally what's considered the final phase of the Wisconsin Ice Age, which is usually called the late Wisconsin, really got active around 26,000 years ago. So it is quite well documented that if you go back, say, 30 to 40,000 years ago, the vast ice complex was considerably contracted from what it was at its late glacial maximum around 18 to 20,000 years ago, you see. So, but the question remains, and it's a question we're going to examine in more detail, is how extensive was that recession or contraction of the ice masses in that interval, generally referred to as an interstadial. Do you remember those terms, guys? Glacial, interglacial, stadial, interstadial. Right. Glacial, interglacial, and then stadial, interstadial. So you'll have fluctuations of extraordinary magnitude, such as the shift from full glacial, which was the late Pleistocene, into interglacial, which is now, which is a very much contracted version of the ice sheets, the planetary ice sheets. Although we know that there have been episodes where the ice globally has been far less than now, meaning that sea levels have been 20, 30, 40 feet higher than now frequently throughout Earth history, which would then imply even less ice than now. Full glacial, what we could do is, for a rough concept, we could basically double the amount of glacial ice on the planet now to get the amount of glacial ice in the late Pleistocene. Or I should say, the Pleistocene is the 2.5 million years, but the late Wisconsin is the last phase of ice growth in North America. And in North America, in Europe, it's the Fennoscandian, but the Fennoscandian ice sheet, which was actually the Weschelian ice phase, which the Weschelian coincides with the Wisconsin in North America. So the Weschelian in Europe was the name given to the last phase of ice growth. The ice sheet itself was called the Fennoscandian. Just like in North America, the last phase of the ice age was the Wisconsin, but the ice sheets themselves were the Laurentide and the Cordilleran. Got that? Okay, so people are clear on that. So there was a late Wisconsin interstadial where the climate warmed. And somewhere between, say, in 30 and 40,000 years ago, there were extensive forests growing in Canada, where 10,000 years later, there was extensive ice sheets. Now, the question is how much was the totality of glacial recession in that interval there compared to now? And of course, another auxiliary study that would help one understand that would be studies of sea level. Because obviously, the more the ice is reduced on the land, the higher the ocean level is going to come, right? So when we look at this problem, we're not only going to look at evidence for what the ice was doing on the land, we're going to look at evidence for what was going on with sea levels. Because as the ice is growing on land, sea levels are falling. When ice is shrinking on land, sea levels are rising, right? So we have this, it's almost like a breathing in, out or something, but we can see that this has happened many times throughout the Pleistocene. And in fact, that is really could be the signature phenomena that characterizes the Pleistocene, is this glacial expansion and contraction repeatedly that didn't seem to be going on in the previous epoch, the Pliocene, at least certainly not to the extent that it began to do once the Pleistocene got underway around 2.5 million years ago. So interesting questions. Now, I guess let's see. We're getting at. I'm going around here. I'm trying to get back to my original thought, but the Tunguska event. Okay, so the Tunguska event, we're looking at an event that would be very much an analog for what might have happened during the Younger Dryas. And so, at the Younger Dryas, we've got to get the picture in our heads. Somewhere around 26,000 years ago, whatever that was there, either probably there was some ice, but drastically reduced. It began to expand. It expanded and grew and grew. The sea levels went down. Between 18 and 20,000 years ago, it appeared to have been the LGM, the late glacial maximum. Then, over a period of a couple of thousand years, and this, as I've been going through the literature, I find that there's no real agreement on at what point did the late glacial maximum really begin to significantly shrink back. Some studies would suggest that it was around 15,000 to 16,000 years ago that it began to shrink back. But slowly, more gradually, and this slower gradual shrinking back could be considered, if you think of it this way, could be thought of as being driven by the much slower astronomical changes, what is the so-called Milankovitch phenomena, which depends upon precessional motion. It depends on the obliquity of the ecliptic. It depends on the eccentricity of the Earth's orbit, and how these things interact will change the amount of solar radiation reaching the surface, sometimes increasing it, sometimes decreasing it. The expected result of that is that when the solar radiation heat is diminished, ice is going to grow. When it increases, ice is going to shrink. Now, when we get to the end of the late Wisconsin, which would have been, say, between 13 and 15,000 years ago, what we're seeing is a shrinkage of the ice sheet that would be consistent with the shifting Milankovitch forces, you see. But then what happened is this thing around 13,000 years ago, where that was suddenly interrupted, you see. And so it's very possible that in that period of shrinkage, where perhaps 10 to 15% of the ice mass was lost, right? That is when you may have had the opening up of the ice-free corridor on the western prairies of Alberta, just east of the Rocky Mountain front, that is now defined by the foothills erratics trade that we've talked about a bit, right? So that's very possibly a time when the Cordilleran ice sheet and the Laurentide ice sheet might have opened up enough to allow the migratory movements of both animals and people, right? But then that sort of more orderly, typical, it was a sort of predictable shrinking back of the ice sheet. Then we get to the significant event, the turning point, which now is actually dated closer to 12,800 years, where there was a sudden spike, a huge spike of warming, followed by this return to 1,300 years of cold that then came to an end around 11,600 years ago.
Is the older Dryas at the late glacial maximum? Is that when that was?
The older Dryas falls between the Bolling and the Allerod.
Okay.
Which is right around, I think, 14.6, 14.7, very close to that, the age that's now usually given for meltwater pulse 1A. So that point, to me, is a turning point also at 14.6 to 14.7 that really, I think, needs more scrutiny. And I would like to dig up and see what I can find on, events around that time. The meltwater pulse 1A, because see, that may have marked the first phase of the great glacial meltwater floods. That might have been the first flood that, say, went through the Scablands. But now, from the work of Teller and others in Lake Hind, which we're going to look at, we're seeing that there was catastrophic flooding there that dates right to Lake Hind is in Manitoba, and there was catastrophic flooding that took place there pretty much right at the Younger Dryas boundary, which we've been exploring it, or where we're moving with this is exploring the idea that the Younger Dryas events, impact events, somehow may have been involved in triggering these mega floods that occurred at the end of the last ice age. And somehow the combination of effects of the impact, or maybe even episodic impacts. See, this is the thing where I think we would need to be looking at. Is it possible that we had a bombardment epoch between that Pleistocene-Holocene transition, where there may have been several episodes of bombardment? I think seriously we need to really be looking at that model, with perhaps the first bombardment phase at 14.6 to 14.7, another bombardment phase at 12.8, 12.9, and then perhaps even a third at 11.6. Because at each one of these, we find things happening that really, in their own way, are sort of inexplicable, right? Because when you start looking at these mega floods, the amount of energy necessary to melt so much ice to create literal tsunamis of meltwater sweeping over the land is pretty phenomenal. And where that energy is coming from is a very perplexing question. Now, is it the sun? I don't know. I don't rule out the sun. But what does that, if it's the sun, like, so let's say, just hypothesize, 14.6, 14.7 years ago, could there have been some hyperactive solar event that caused that first melting episode? I don't know, because, but I would think it would, something either that or an impact would be the first two most likely things that would come to my mind. I don't know how you would go about proving that it could have been a solar event unless you could find maybe deposits of radiocarbon 14 and beryllium 10. I don't know if anybody's looked for that yet. And then we've got the 11.6 event. So right now, all of the Younger Dryas boundary stuff is focused on that 12.8, and that's where all the proxies are being found that we've been looking at. That's where the biomass burning is being found that we're looking at. Okay, so anyways, to come back to Asteroid Day, I think what we're seeing is we have to look at various phenomena that might have parallels to what happened at the Younger Dryas to try to get a better handle. And here, the Younger Dryas, the Tunguska event of 1908 is a supreme teaching episode from which we can learn a considerable amount of information. Like we were talking about earlier, the timing of it was interesting. 1908, because of the fact that seismographs and barographs had only recently come online, and because of the presence of seismographs, we're able to document the seismic consequences of an aerial burst. Now, that's a pretty interesting thing to find out that there's like a 5.5 earthquake generated by an aerial burst 5 miles up in the air. The other thing was, and so understanding that there were actually these terrestrial consequences of an airburst has taught us a whole lot about the nature and power of this event. Okay. The other thing is the presence of barographs, which will measure changes in atmospheric pressure. And because of the presence of the first newly installed barographs in England, there was a documentation of two pressure pulses that passed around the entire planet as a result of an explosion over Siberia. Knowing that there were these pressure waves in the atmosphere that literally encompassed the entire planet twice, again, has given us considerable insight into the nature of that event that we wouldn't have had it happened 10 to 20 years earlier. See? The other thing interesting about that is its location, because if it had happened just maybe 100, 200 miles further north, it would have been over tundra and not taiga. But because it was over Tioga, where there's old growth forests, now we get to see the effects of the blast in terms of the radial tree destruction, right? So a lot of data can be extracted from that. A lot of inferences can be made as to the power of the event, able to measure the actual square area of the destruction, right? Again, if this had happened 100 or 200 miles further north, we wouldn't have probably ever known about it. Now, see, even though the scientists in England saw the pressure waves passing over England, they didn't know what was causing that. It wasn't until over 20 years later that the dots were connected. Oh, June 30th. Yes. Atmospheric explosion in Siberia, pressure waves encompassing the planet twice. And I think they were separated. I think it took 11 hours to make the full journey around and come back again. I've forgotten the specifics, but when we get into our extended analysis of the Tunguska event, I'll have that data at my fingertips. So let's look at the, let's see, let me get my screen up here and we'll do a share screen.
I just wanted to say that if you take the length of the solar cycle, right, 22 years.
Yeah.
And you want to divide that in to get roughly, what was it, 14,700 or something?
14
years ago?
Yeah, say 14.
So I'm basically, if you multiply it times 666, you get 14,652 years ago. Just saying.
Well, you may have inadvertently stumbled upon something there, Kyle, but I don't know. I think you'd better devote a couple of years to researching that and then get back to us on it.
Will do.
Okay. Wait, so what was it again? If you took the 22-year cycle times 666,
yeah.
Was it 22?
Yeah, it puts you
14,652. There we go.
See, that's devilishly clever arithmetic.
That's right.
It's, yeah.
We are in a deep solar minimum.
That proves it, Kyle.
Yeah.
That proves it.
Dr. Shock was right.
What it proves, I'm not sure. Dr. Shock, how did he get into the conversation?
The sun. It's the sun, man.
The sun. Okay.
Sorry for the distraction.
It's okay. I need a distraction every now and then. Okay, so we'll do a share screen. And why?
Well, 666 is all kind of related to the sun to start with, and that can be a whole show on its own in the future.
Oh yeah.
More.
Okay, here we go. Here we are. There it is. So just to get everybody kind of oriented, we have Siberia, and this area right here, all of this area is part of the Siberian Traps, which was this great magmatic outpouring that was coincidental with the Permian-Triassic boundary events and the greatest upheaval mass extinction in the history of biological life on Earth. So here's Lake Baikal, which is part of this rift system here. But so right there, which shows where the event happened. And this was one of the first papers in English that was published in 1934 after the discovery by Leonid Kulik. And this was a Russian scientist who studied the site, published this in the Quarterly Journal of the Royal Meteorological Society. Airwaves caused by the fall of the meteorite on 30th June 1908 in central Siberia. The flight and fall of the meteorite on 30th June 1908, amongst the greatest meteoric phenomena known to mankind, must occupy one of the foremost places because of the magnitude of the phenomena accompanying its movement through the atmosphere. If it had occurred 4 hours, 47 minutes later, when the city of Leningrad would have lain on the same parallel near the center of the explosion, our knowledge of it would probably have been considerably more extensive.
What about understatement? Lord have mercy.
Really. So I'm going to show this very briefly here because this is essentially a very abstracted map of the southern sky on June 30th. However, what is placed in there are the radiant points or the positions in space out of which various objects would be seen to emanate. So, for example, up here on the upper right, you have Earth approaching comets. And so each one of these represents the position in the sky from which an Earth approaching comet had been documented. And what we look at the letter Z in the circle. This is the position in the sky on that morning where the Tunguska object emanated from. And you'll notice that it's very close to the rising sun, which is rising here in the east, but it's even closer to the radiant point of the Beta Taurids right here. Up here are the Zeta Perseids. Geographos is an interesting object we can talk about at some point. Adonis, Icarus, the Aratids is another meteor stream. These are asteroids. And so what's interesting here is the proximity of the radiant point from which the Tunguska object emanated. And this is based upon the most exhaustive studies of the angle of approach as indicated by the blast pattern of the trees, coupled with extensive interviews with eyewitnesses. In the early days in the 30s, a lot of them were still alive, so it was possible to interview them, collect together a lot of data on where people first reported seeing it, where they were standing when the event exploded, and so forth. And by means of collecting this data, it's possible then to sort of trace it back to the position of where it would have emanated from the sky. And you see here how close it is to the sun. Well, what that means is that when you were looking towards the east in that morning, on that morning of June 30th, you would have been looking towards the sun. And because of that, the object was invisible until pretty much the last moments before it exploded. If it had come, and so you've got two things going on here. You've got the point in space is consistent with it being a member of this Beta Taurid meteor stream, which actually peaks on June 30th, July 1st, right there. So the timing and the placement are both consistent. Now, that doesn't prove that it was part of the Taurid system, but it is really strong circumstantial evidence that it was. And we're going to come back to a discussion about the Taurid meteor system because it's very, very interesting and very important. And we're going to discover that a lot of ancient peoples were also very interested in the Taurid meteor stream. So that's kind of why the assumption is made that it's very plausible that it was a member of that family. And this ultimately would relate back to this idea that we were talking about earlier of a giant comet entering the solar system, inner solar system, say between 25 and 30 years ago, 25 and 30,000 years ago, and then begin to undergo this hierarchy of disintegrations that spawned multiple meteor streams, a couple of subcomets such as Encke and at least one more. Rudnicki is another one. Right. Several asteroids. So there we go. So let's go to the next one. And now this is a juxtaposition of two. I just grabbed this off the internet to show people, but this is probably the most famous photograph associated with the Tunguska event. And of course, you see the trees. The size of these trees is roughly 3 feet in diameter. So you had this vast area of devastation caused by the explosion. And if we go back here, it's showing the area and how the arrows are pointing in the direction that the trees are laying. So in other words, the tops of the trees are pointing away from the epicenter. Does that make sense? Because you had this tremendous blast right over this area, and then the shock wave moved out radially in all directions. And as the shock wave moved out, it just mowed down the trees, just snapped them off, and they flew down. It's estimated that somewhere around 82 million trees were instantly snapped off. That's pretty bizarre when you think about it. 82 million trees. It's a lot of damn trees. Right? Here's another photograph. So this had been old growth forest, and then, moments later, it looks like this.
And they're not just blown over, all the branches are gone. It's, it looks like they've been stripped almost.
Right. And then when you get to the epicenter, it's basically just a barren zone. And then just outside the barren zone, you got a picture that the blast wave, now the estimates is that the detonation of this object occurred 5 or 6 miles, say, above the surface, right? So you've got a picture that this blast wave is coming down. The epicenter is going to have the pressure coming down vertically, and it's going to hit the earth, and then it's going to move laterally. And of course, it's going to be super hot. It's estimated that the center of the fireball at the peak of the explosion, it was 10,000 degrees centigrade. So that's hotter than the surface of the sun. So that's pretty damn hot, right? So pretty much it created 200 square miles of combustion, instant intense combustion that pretty much left not much of anything. Outside of that blast zone, there's a ring of trees, which you can see right here, that were left vertical, right? But their branches were mostly stripped off. And then outside that ring, you start finding the trees splayed out, laid over, snapped off. So you can, because of the tree pattern, it's kind of almost possible to trace the movement of the blast wave as it comes down, strikes the earth, and then radiates out in every direction, 360 degrees. So before I go to that, we'll do this. The total area of devastation that you see here in this was over 800 square miles. The area of incineration at the epicenter was about 200 square miles. So within that 800 and some square miles, now think about this. So a 30 by 30 square would be 900 square miles. I think the area of devastation is estimated to be about 820 to 830. So you're talking about almost, if you picture a blast zone that's, going to be 28 miles or so. Let's see, we can do 825 and we square root it. That's almost 29 miles, right? That's a pretty healthy distance, isn't it? 29 miles. So if you picture a square area, 29 miles in every, on all sides, and within that area, pretty much everything is destroyed. That is a powerful blast. Now, how powerful? So what I've done is just to show a few images of nuclear tests to try to get an idea, because the estimates for the energy release during the Tunguska event are generally around 15 megatons, which means 15 million tons of TNT, right? A megaton. 15 million tons of TNT. Now, how much power was in the atomic bomb that was dropped on Hiroshima? About 15 kilotons. So 15 kilotons is 15,000 compared to 15 million. Now, so 1,000 Hiroshima-sized bombs going off at once would give you about a 15 megaton explosion. Now, 15 megatons, Castle Bravo. I'll show you a picture of it in a minute. That was the largest nuclear bomb tested by the U.S. during the Cold War back in 1954. It was about 15 megatons. So interestingly, here's another perspective on this. Tunguska was at the bottom end, right, of the cosmic range of energy is released. Maybe if we step it down one more, we'll have Chelyabinsk of 2014, right? A step up from Chelyabinsk, and you're at Tunguska. A step up from that, now we're really getting into, we're talking about objects, that might be, 4 to 10 times more massive than Tunguska. And now we're getting into an object that, let's say, Tunguska, we could call that a city killer. And I'll show you just, I've taken a map of Atlanta and superimposed this area of destruction on that, which I'll show you in a minute. So that, but you'll be able to roughly compare. Atlanta's, going to be the same size metro areas as most of the other major cities in the U.S., right? So 15 megatons. Now, the largest hydrogen bomb ever tested by the human race was Tsar Bomba, which was 1962, and that was the Soviet Union detonated a bomb in Siberia, as a matter of fact, and it was estimated to be 55 megatons. But thankfully, we got through that intense period of the Cold War without committing mass suicide. That's another subject we should talk about, since we're actually sort of in a new Cold War with Russia, even as we speak. Not a good development, but anyhow. So let's go on, and we'll start. We'll look at a few actual photographs of nuclear explosions. I've taken from the French testing, because the French continued to, they tested atmospherically, up to, years after the U.S. and the Soviet Union had quit testing. These U.S. signed the Limited Test Ban Treaty in 1963, and this basically limited nuclear testing to only underground nuclear tests and not above ground atmospheric tests. And the Soviet Union and the U.S. tested that, signed that treaty. The French did not sign it. So they continued, and they developed their own nuclear program, and then did a lot of testing, around the turn of from the 60s to the 70s. So this first photograph is going to be from Bikini Atoll. Oops. And it's going to show a 1 megaton explosion. Actually, a little bit less than a megaton. And this is an actual photograph. Here it is, July 3rd. So it actually, interestingly, occurred during the Taurid meteor shower, because the Taurid meteor stream of the Earth actually takes almost a full week to cross the Taurid meteor stream. So here we have the French nuclear test carried out on Fangatofa Atoll, July 3rd, 1970, yield 914 kilotons. So remember I said Hiroshima was 15 kilotons, if that. So 914 divided by 15. This thing is then 60 times more powerful. Is that right? Yeah.
Pretty
Than
close.
the Hiroshima bomb. Okay, so this is a little bit less than 1 megaton. Now, 15 megatons, now we're talking about 15 times greater than what you see right here. Red Wing Dakota, which was a test in 1956, a little bit more than a megaton, 1.1 megatons. So this is a pretty damn big explosion right here. You can see it. It's the mushroom cloud is advancing up into the stratosphere. Another 1 megaton explosion, like LeCorne nuclear tests on Fangatofa Atoll, 1970, yield 1 megaton. So again, 15, the largest hydrogen bomb in the U.S. arsenal ever tested, 15 times more powerful than what you see right here. And now we're getting up into the range of the lower range of cosmic energies. You see, so as we go up the scale in the power of controlled by humans that we see represented right here, we're getting into the bottom end of the energies generated during even a small cosmic event. And now we're up to 4 megatons. So we really can see here that the whole mushroom cloud, the fireball, is rising right up into the stratosphere. And then finally, here's another one of another photo of Castle Romeo. This is nice. So now this, of course, is the U.S. And then we have the largest hydrogen bomb tested by the U.S., Castle Bravo, 1954, 15 megatons. Now, I found a really cool painting on the internet that would show, to give some sense of scale, a 15 megaton explosion, say relative to a typical urban area the size of Atlanta or New York or Washington or Detroit or Philadelphia or any of the major cities, right? One more image of the Castle Bravo, largest hydrogen bomb tested by the U.S. And you can see here, it's going right above the cloud layer, right up into the stratosphere. Okay, so now the next image will kind of give you the sense of what a 15 megaton explosion would look like, juxtaposed on a major urban area. So what you got to take away from this is that we had a naturally occurring explosion in 1908 that was on this scale right here. And right under the fireball would be where the 200 square miles of combustion destroyed everything, and then radiating out from that for another 15 to 20 miles in every direction was the blast wave that mowed over the forests. So that's why we would call that a city killer.
Randall, are these, the photos you're showing, are these air bursts or surface bursts?
They're probably surface bursts. There was a whole series of tests done, some done for surface, some aerial bursts, some actually below the ocean, and some underground. While we're looking here, maybe Kyle would look up Castle Bravo, 1954, and it'll probably tell us. I think a lot of the testing were mounted on towers, and then of course detonated remotely.
Yeah, but on these particularly the ones on the atolls in the South Pacific, my thinking is that they were probably surface bursts, like out on ships or on the atolls themselves.
Yeah, but I think they were mounted on towers, and maybe
Okay.
Kyle will tell us here if he. Castle Bravo, 1954.
Yeah, we're looking.
Aha.
We are looking it up.
So here is the map of Atlanta. Here's 285, which is very close, let's say, to the perimeter interstate that surrounds Washington, D.C. and area. Okay,
it's about 65 miles in circumference.
In circumference. Okay, interesting.
Okay, it says the device was mounted on a shot cab on an artificial island built on a reef off Namu Island.
On a what?
Shot cab. I don't know what that is, but
shot cab.
Yeah, so it was mounted on something close to the ground. Probably it wasn't dropped or anything.
No, it wasn't dropped. It was definitely not dropped.
Right.
A shot cab. Okay, I wonder if that's what they're calling. It undoubtedly was mounted on some kind of a device. The question is how high up off the ground. Now, when Trinity was detonated, which was the first atomic bomb, plutonium bomb, that was detonated in New Mexico, it was definitely on a pretty tall tower. So it was not actually on the ground. And the Hiroshima bomb was detonated in the air because of the fact that the radius of destruction is greater when the explosion occurs in the atmosphere than when it actually strikes the earth, because so much of the energy is absorbed in the impact into the earth itself, which sort of localizes it much more so than when the energy is free to expand outwards as it is in the atmosphere. And so Hiroshima was detonated in the atmosphere in order to generate maximum destruction, maximum death and destruction. So here's the city of Atlanta, 285, the perimeter highway. And then what I'm going to do is I'm going to superimpose that butterfly-shaped area of devastation over the city so that you can kind of get a sense of the scale. So you can see that pretty much the area of destruction is very, very close to the area inside the perimeter interstate. And since this perimeter interstate is similar to many of those in other urban areas, large urban areas around the U.S. Or Europe for that matter, you can see that this is why it's referred to as a city killer, because it's large enough to pretty much wipe out any large city on Earth, were it to explode, say, over that city.
I just wanted to throw in the shot cab is the name for a large corrugated aluminum building where the bomb is mounted.
Mounted, okay.
It's what they call the shot cab.
Okay, and so so
it must have been just on the ground in a building.
Yeah, but undoubtedly it was mounted on something in a building. Yes, in a building. Probably not just sitting right on the ground though. Just sitting in the dirt.
I have seen the image of the ones from the towers because it incinerates the guide wires that were holding the tower, and you can follow that along with the mushroom cloud going up. You see these orange streaks shooting down, and it's the guide wires are just being instantly incinerated.
That are stabilizing the tower.
Correct.
Yeah. Okay. Cool. Yeah. So by looking at our own experimentation with nuclear weapons helps us to understand the kinds of forces we're talking about here with these impact events. And the thing about these impact events is that, there's a scaling ratio in that the smaller the object, the more frequent we can assume that encounters with those size objects are going to be. So the question is how often does the Earth encounter a Tunguska-sized object? So we can make assumptions about that. A lot of those assumptions have been, if we just sort of randomly encounter objects of that scale, maybe once every 100 to 200 years, I think is a very typical periodicity that I've seen. But now to this, there's no particular repetitive pattern or periodicity. In most of those assumptions, you could say, Tunguska was just a random event. Now, how often do these random events happen? Well, maybe on average, a century every 2 centuries. Of course, even there, that would imply that, when is the next Tunguska scale event going to happen? And when it does, it's a different world now than it was in 1908. A lot more people live in, what would have happened, like in that quote that I read from Astapovich, what would be the effect if it had happened 4 hours and 47 minutes later? Well, it would have wiped Leningrad off the map. Well, if that had happened, it's very possible that 20th century history would have been drastically different. Certainly, right? Probably. And our awareness of threats from space would have been well established in the human psyche, 4 generations, 5 generations ago. As it is, we've gone blithely along, oblivious to what's happening over our heads, unlike our ancestors, who we will show everywhere were intensely concerned about things going on in the heavens. Now, what we need, I think, to be cognizant of is the fact that if, for example, the Tunguska event was part of the Taurid system, then that opens the possibility of there being periodic events. Because the question is, if Tunguska, which is estimated to be about, say, 50 meters in diameter, that's not really big, I mean, if it was sitting on the ground, you'd go, yeah, that's a hell of a big rock or a big snowball or something in between, right? But, think of that, 50 feet, that's a 5-story building, right? So, yeah, it's big. You wouldn't want the thing to land on you. But in cosmic terms, it's pretty tiny, right? if you set it next to an object that was half a mile in diameter, it would just be this little thing next to this, right? An object a half a mile in diameter now, that's going to be an object that could wipe out an area the size of Texas, as an example.
No way, bro.
Not possible to wipe out Texas.
Well, at least not while you guys are living there anyway. So, but Tunguska about 50 meters, so say 150 feet in diameter. Well, Tunguska object being presumably a cometary mass is going to be at the low end of the density spectrum, close to the density of ice, maybe a little more, depending on what constituents, what was it composed of. But if it was pure ice, then it would be about, roughly a gram per cubic centimeter. On the other end of the spectrum, we have the iron asteroids, which is a whole family unto themselves. And then, and they're about 6 to 7 grams per cubic centimeter. So picture, if you will, think about this. In this hand, you're holding, let's say, a chunk of ice, right? And in this hand, you're holding a piece of cast iron. And that's the difference in range right there. And then in between, you've got a full gradation of different densities, with chondritic asteroids being roughly right in the middle, right? Stony asteroids being generally a little bit more dense than the chondritic asteroids, I think, in most cases. So you figure, okay, you've got a chunk of ice in this hand, you got a piece of cast iron in this hand, and then in your third hand, you're holding a stone, basically a typical rock. That is, if you are from Zeta Reticuli, because they have 3 arms. So they could be holding a rock in the middle that would be a typical rock, 3.5 grams per cubic centimeter. So that's pretty typical. And each one of those coming into the atmosphere at a high rate of speed is going to have a different kind of effect once it impacts. Now, the lower the density, the more likely it's going to be to not be able to penetrate the full atmospheric column and strike the ground. The high density objects are going to be much more likely, even the small ones, to penetrate the atmosphere and strike the ground. Now, once you get up to about 1 kilometer in diameter, even the low density ones are going to penetrate the full atmospheric column and strike the ground. Although probably an object 1 or 2 grams per cubic centimeter, when it strikes the ground, is going to leave a different suite of features than one that's 7 grams per cubic centimeter, you see? So there's a lot to sort out here. And then on top of that, you've got the angle of entry. You've got the nature of the target rocks. All of that stuff. Speed. What happens with oceanic? See, now, as we were talking about earlier, there's pretty close to about 200 now confirmed and probable impact craters around the surface of the Earth. And the vast majority of these are terrestrial, right? And yet the continental land masses are only a little more than a quarter of the Earth's surface area. So it would be safe to assume that if there's 200 confirmed so far, and, undoubtedly there's going to be more, what's hiding under look what just has happened in the last few years. We've discovered potentially 2 craters hiding under the Greenland ice, right? Are there craters under the Antarctic ice? Are there craters that we don't know about, Brazilian rainforest? Are there craters that are, or astroblems that might be buried under even a few hundred feet of sediment, so we don't really see them? Or in the case of the KT impact, the Chicxulub impact crater in Mexico, it's under almost a 0.5 kilometer of limestone, because it happened 66 million years ago, and you've had in a shallow marine environment where you have accumulating limestone rock. So it's certainly safe to say that at some point we may reach 250 known or probable impact craters, astroblems, terrestrial. But then we have to assume that there's going to be 3 to 4 times as many impacts into the oceans, right? I mean, unless you're going to argue to me that the influx of these objects is selective over terrestrial targets, and I don't see any evidence of that or any reason or logical reason to make that assumption, we then have to assume that for every 1 impact, boom, into the surface of the Earth, there might be 3 or 4 impacts into the oceans. So we need to now be thinking about what are the consequences of an impact into the ocean. And of course, there are a couple of things, a couple of factors. One is the impact, is the object large enough to penetrate the full water column and strike the floor of the ocean, or is it going to basically vaporize in the water column itself without actually penetrating the ocean floor? So that would be a consideration. Now, if you had one that actually excavated a crater on the ocean floor, well, now what you've got to say, okay, well, here's the crater. Now, what's going to happen because it's on the bottom of an ocean rather than, say, a crater on land? Now, and we know on crater on land, there's an impact, there's a pressure wave that moves out, and then that creates a vacuum and it collapses back in. And we know that breccia will be thrown up into the atmosphere and fall back into the crater, while at the same time there will be a strewn field around the crater where the fallback material mantles the landscape. If the object comes in at an angle, it'll actually preferentially eject the impact material in the direction from its trajectory into the atmosphere. So it will not be radially distributed around the point of impact. It will be, it'll be distributed around in a pattern, probably elliptical, right? So, but what happens in an ocean event? Well, you'll have the ocean will open up. There will be a transient crater produced, just like there is in the ground, except now, once that outward moving pressure diminishes, then the water column will collapse back inwards. Of course, now when it's collapsing back in, it's going to be carrying a whole lot of sediment back in with it. And all of that water, in fact, it's even been given a name, the resurge wave. So the resurge wave is going to collapse back into the submarine crater, and it's going to bring a lot of sedimentary infill with it. And if there's a raised rim around the crater, that inrush of water will tend to smooth out and lower or eliminate the rim altogether. So it's going to be harder to identify impacts into the oceans for that reason. However, I will predict that as we get more and more, we've mapped now about in detail about 1/4 of the ocean's floor. We've got 3/4 of the floor to go, and I don't know yet because I haven't had an opportunity to look to find out if anybody's actually going, okay, now that we're getting these detailed maps of the ocean floor, can we study these maps to determine if there is indications of impacts? And again, the problem here is because if you start looking for what you'd expect to find on land, you may miss it because it may be a different phenomenon altogether. Now, if the object is not big enough to actually penetrate the full water column and excavate a crater on the ocean floor, then what are you going to look for?
And I know you're going to get into this again because it links directly back to Tunguska, but there's a whole much larger number of the ones that are air bursts. So
yes.
It's going to move some water out of the way, or it's going to create a shallow crater, and in 1,000 years it's going to be gone, and we're going to have no evidence.
Right.
So I know you're going to. Yeah, you're going to jump into that some more, but I'm just want to say we're about an hour in, so if we can slow down, take a break here. Are you ready for a break?
Sure, ready for a break.
Let's halt, and we'll be right back.
Okay.
All right, welcome back, ladies and gentlemen. I guess we're going to wrap up this Asteroid Day extravaganza. Where are we going next there, Randall?
Well, Kyle, I thought perhaps we would just do a very quick run through of a group of craters to give people an idea of some of the things that have been documented and look at some of the astroblems, the actual stars in the landscape with relative energies of these events. So we will do our share screen and we'll do this. Okay. So this is the famous meteor crater in Arizona. I got approximately 26,000 years old here. I don't know if that's correct. Most of the estimates I've seen are 40 to 50,000 years. I think there have been some studies suggesting it's a little younger, though, like at the age I've got here. The age is not so important right now. The main thing is to understand is that this was created by the impact of an iron object. So interestingly, it was about the same size as the Tunguska object. So it kind of gives us a means of comparison. And of course, the difference being the much greater density of the meteor crater in Arizona, that meteorite is why it hit the ground and created this hole in the ground that's just obvious to anybody, and why Tunguska did not create a hole in the ground like this. So estimates here are about 20 megatons. So given that the estimate for the Tunguska, I used 15 megatons because that's the one usually cited, but there have been estimates up to 30 megatons for the total energy released by the Tunguska event. I think most of the estimates that I've seen range from around 12 to up to 30 megatons. I kind of stayed the more conservative side, which is 15 megatons, which I think is closer to the majority of the estimates, but certainly it gives some idea, gives one the idea of the destructions involved. So we're going to just run through here looking at just a gallery of some various impact craters, along with some sense of the energies released. So Lonar, India has a lake in it, about 500,000 years old. It's 1.1 miles in diameter, so that's certainly bigger than the meteor crater, which was the one we just looked at, which is 3/5 of a mile in diameter. So this is just roughly about twice the diameter. And I've got there 20 megatons, which is actually on the conservative side. It might be closer to 25 or even 30 megatons. That happens to be about roughly 1,400 Hiroshima-sized atomic bombs exploding at once, just to give you some sense of the power. This is in Ontario, Holaford crater. Now, this one is very obscure. It's almost more of an astrobleme than a crater because it's definitely a scar, but it's healed a long ways because it's obviously become eroded, infilled with sediment. But you can certainly see the circularity of it. And it's a very old one, so that's consistent with its degree of erosion. As it says here, diameter 1.46 miles. At that point, the explosive energy is about 42 megatons. So now we're getting up into the range of Tsar Bomba, which I remember I said was 55 megatons, which was the largest hydrogen nuclear bomb ever tested during the Cold War by the Soviet Union, which was more than 3 times the power of Bravo, which was the U.S.'s largest hydrogen bomb. 2,800 Hiroshima-sized atomic bombs exploding at once. Australia, this is a really old one, diameter about 2 miles. So this is like, again, a scar, an impact scar, an astrobleme. Astrobleme literally translates as star wound. So we're up to about 125 megatons for one that size. The BP structure in Libya, which is about 120 million years old. It's almost 2 miles in diameter. So it's going to be about 125 megatons, right in that range. Some of these are old. Here's a better shot of the same BP structure, maybe with some recalculations, because probably the other one was an older version, because I've been putting these things together maybe for 25 years. So sometimes I update them, and then other times I don't update them, and some of the information may have become updated in the process but the point here is not the precise details of this, but in this case, what we're looking at is to try to get a general concept of the energies involved. I've always been fond of this. Steine Basin in Germany, about 14.8 million years old, 2 miles in diameter. There's actually 2 villages built right inside the crater. And notice the flatness of it in the farmland, which shows that the crater has been infilled with a lot of sediment. So this would have been roughly about 8,000 Hiroshima bombs exploding at one time. We come up Brent Crater in central Ontario. also about 2 miles in diameter. Now, a lot of craters in Canada, and I think one reason for that is that because of the successive glaciations over Canada, a lot of the upper layers of the bedrock have been scraped away. And so they've kind of exposed some of the astroblemes that might otherwise be more obscured under the top layers of rock. And you'll notice that a lot of them do have lakes in them. And here you can very clearly see the circularity. And this is probably the inner part of the crater. There may have been a raised rim around here. Chubb Crater, northern Quebec, also about 2 miles in diameter, and it's an almost perfectly circular lake. This is Flynn Creek structure in Tennessee, which is kind of in our backyard. And this is probably one of the 34th parallel chain of craters, which we're going to look at and talk about in detail, because right across from east to west in the mid-central region of the United States, there's an interesting array of craters and crypto explosion structures that are almost aligned in a pattern. Some of them are proven to be impact. Now, this is the Flynn Creek structure, and this is just a digital elevation model, but very clearly the central uplift peak shows up. The rim is highly distorted, probably because of tectonic processes, because it's a very old, about 360 million years old, 2.2 miles in diameter, 180 megatons or 12,000 Hiroshima-sized bombs. Goat Paddock in Western Australia, imprecisely dated, less than 50 million years old. Now we're up to 3 miles in diameter, explosive energy about 500 megatons. So we're getting up into some serious energy here now. 500 megaton explosion, we could consider that a state killer. An object like that striking the center of Texas is going to be pretty much leave most of Texas depopulated in the aftermath. Gow Creek Crater, Saskatchewan, 3 miles in diameter. This remnant of the central uplift is an island. Notice how the rim has been so obscured and eroded. Well, for two reasons for that. One, the glaciation itself, and then the rapid melting of the glacier and very vigorous meltwater currents also contributing to further extreme erosion. But the feature is still there, and it can actually be roughly dated, but it's less than 250 million years old. So Pilot Crater, Northwest Territories, again, we're looking at Canada, 3.6 miles in diameter, explosive energy, over 1,000 megatons now, 1,060 megatons. And this is based upon a simple formula that only gives you approximately a ballpark idea of the energies. And it's basically a formula that's derived from known impacts and nuclear explosion energy released, craters produced, etc., to come up with a simple ratio between crater size and impact energies. But of course, there's a lot of variability in there, depending on the nature of the impactor, its velocity, the nature of the target material, and so on. So this is only just a rough approximation, but it does give you the idea. It gets you in the ballpark. Decaturville, Missouri, diameter 4 miles. That puts us up there again in that 1,000 plus megatons. The Decaturville, Missouri structure is also one of these 34th parallel crater chain that we're going to look at in more detail. Brad and I have actually visited several of those. I think maybe even 3 of them, of the 9 or 10 of them. Crooked Creek, Missouri. This is another one that could be possibly related to this crater chain. It's 4.34 miles in diameter. Check this out, 1,792 megatons. So that's 120,000 Hiroshima bombs all exploding at once. So we're getting up to some pretty significant energies. Another one, Couture, Quebec, Canada, 5 miles in diameter. At 5 miles now, we're up to 2,800 megatons. Now, during the peak of the Cold War, the entire nuclear arsenal of both the United States and the Soviet Union is estimated to have been roughly around 10,000 megatons. All thousands of warheads. This would have been in the 60s and 70s. But of course, what happened was as the Cold War and the arms race evolved from the 50s through the 60s to the 70s, the strategy went from mutual assured destruction, relying on the ability to deliver one nuclear weapon. If you deliver a nuclear weapon of 10 megatons or 15 megatons, well, what's going to happen is one bomb is going to wipe out the entire city, right? But it's not very precise. I mean, when you're looking at a bomb of that scale, it's not pinpoint precision is not really too critical. It's really what you're doing during mutual assured destruction doctrine. The idea was each side was holding its cities hostage. It was holding its urban areas hostage. Well, if you attack us, we're going to wipe your cities out. Now, throwing a 10 megaton bomb at a city, it's not going to matter really whether it falls on point A or point B a mile away. The city is gone. You follow me? So what we see as the arms race evolved from the 50s through the 60s into the 70s is that the size of the nuclear warheads decreased considerably. Why? Because the strategy went from being able to wipe out an entire city to being able to take out a specific target with a high degree of accuracy, you see. But in order to do that, the throw weights riding on the delivery systems, the missiles, had to be reduced, because the throw weight of a 10 megaton bomb is such that there's no way to incorporate it and integrate it with the really sophisticated guidance systems, like, say, if you were using a 100 kilo or 200 kiloton weapon. So, but of course, now when you've reduced the size of the warhead, what you do is you can increase the number of warheads. So part of the evolution of nuclear strategy was you decrease the size of the warheads. And now, you see, in the early days, you had one delivery vehicle, a rocket, and you had one warhead mounted on that rocket, right? As it evolved, they developed systems where you could mount multiple warheads on one single delivery vehicle, you see. Now, of course, you couldn't mount 10 or 15 megaton warheads and get 10 of them, a bus of 10 of them mounted onto one rocket, because they were too big. But now reducing them gave that ability to have this multiple warhead delivery system. Of course, now when you're going for precision, you see, you're actually looking at an entirely different strategic doctrine for mutual assured destruction. Mutual assured destruction, again, is the idea is that we're holding your city hostage. You attack us, we can drop one bomb and Moscow is gone, right? So why would you want pinpoint accuracy? What do you think there, Kyle?
Well, you can take out specific targets to reduce threats without wiping out entire populations.
Well, yes, you can. That's the idea. But when you say specific targets, that's the key right there. Because what kind of targets are you looking to take out?
Military targets.
Military targets, exactly. So that was the evolution of nuclear doctrine, to go into these smaller warheads. But see, there's an interesting analogy here, as you're going to find out as we get into this, because what we're looking at here is like one big, like here, what are we saying? 2008. This is like one big warhead. Boom. Right. What we're going to look at, though, is the idea that you might have clustered events where a lot smaller things, like this thing would be 5 miles in diameter, the crater, you can figure that the object that created this crater is going to be between 1/10 and 1/20th the size of the crater that it produces. So if you've got, let's say, 5 miles, which is 5,280 times 5, and we divide that, say, by 15 to put it in the mid-range, we're looking at an object that's going to be roughly 2,000 feet in diameter, right? To Tunguska object was about 150 feet in diameter. Now we're up to 2,000 feet in diameter. See? So the point is once you get to that size, even the low density objects like Tunguska are going to tend to make it through the atmosphere to strike the Earth, you see. So 2,000 feet roughly in diameter. And that's and this is, again, approximate because there's so many variables here, but it kind of gives you the idea. Let's move on, because this is Bagash, I don't know, Kazakhstan, approximately 5 million years old, 5 miles. So here's 2,800 megatons again. We'll keep going. Shoemaker, Australia, named after Eugene Shoemaker, who was studying this particular crater when he was killed in a bizarre accident in the outback of Australia. And I don't have the size of this, so let's see, I might have it. No, don't have it. So, but it doesn't matter. La Moyniere, Quebec, 400 plus or minus 50 million years, 5 miles in diameter, 2,820 megatons. Keep going. This is Upheaval Dome, Utah, less than 65 million years old, 6 miles in diameter, explosive energy. Now we're up to about 6,000 megatons. Remember, I said that the peak of the Cold War, the total nuclear arsenals of the U.S. and the Soviet Union was 10, maybe 12,000 megatons. That was considered to be pretty much enough to destroy the world if it was all unleashed in a nuclear
scenario.
exchange, right? So Brad and I actually visited this one. It's pretty impressive because it's an astrobleme that was undoubtedly buried and has had the top layers of rock stripped away to expose this thing that was, at one time buried beneath the surface of the land. And you see remnants of the old land surface around it in the rim. Look at this central uplift here. So this would be a really cool expedition. In fact, we would add this to the list in one of our undoubtedly future expeditions into the Colorado Plateau and Canyonlands area, because this is in it's in Canyonlands, right, Brad?
Yeah, that's what I was going to add there. That's the Green River right up at the top. So that is within the Canyonlands National Park in Utah, southern Utah.
Right. Sweet. Okay. Eagle Butte. This one's hard to see, but I put in a circle. Again, a lot of these are really obscure, and from the ground, you wouldn't even know they're there. So this is more like an astrobleme rather than a crater, because the scar is still there. And then you do the studies and you find all the impact proxy material, or you find shocked quartz, or you find brecciated rock, which is broken rock, or you might find some melt glass. Many of the different various ways that craters are identified and confirmed. So check this out, 6 miles, 5,300 megatons. Basumtwi in Africa, 6.5 miles, over 7,000 megatons. Now Deep Bay, Saskatchewan, diameter 7.2 miles. Notice 9,950 megatons. So we're now getting up close to the total megatonnage in the arsenals of the superpowers during the peak of the Cold War, which thankfully never got unleashed in an all-out thermonuclear war, or we would probably not be having this congenial conversation right now. So as you can see here, now we're getting up in the scale. This thing is, like it says here, 7.2 miles in diameter. Here's one in Brazil, also about 7.2 miles in diameter, so the energies would have been equivalent. Zhamanshin, Kazakhstan. This is young, less than 1 million years old, 8.7 miles. Notice here, 18,900 megatons. So now we have exceeded, and this thing, if you can see it, it's right in here. Let's see, I might have it. No, I don't. But so now we're well beyond the total megatonnage of the entire nuclear arsenals.
So less than 1 million years ago, there was an event
ago
there that released more than the entire megatonnage of the Cold War arsenal. That's
all being exploded at once
in the same place.
Yes.
Kazakhstan.
In Kazakhstan.
In Kazakhstan. Yes. So you can see that would have been a pretty significant event. So it'd be interesting to look and see if there's any evidence of extreme sudden climate change in this area, any mass extinction events, any biotic turnovers, which I haven't done, but of course it'd be interesting to look, because I would think that an 18,900 megaton explosion would have to have some kind of substantial effects that would leave residuals that could be studied today. Wells Creek, Tennessee. We also visited this one, and there is there's a quarry we didn't get into, but there's a quarry. I think didn't we learn in the Central Uplift, Brad? We met the gentleman who had property adjacent to the roadway into the quarry. Was Wells Creek, wasn't it?
I don't think it was right in the Central Uplift.
Okay.
I think that's the Tennessee River coming across there right at the top.
Yeah. So we didn't get in there. So that's probably worth a return trip at some time. It would be really interesting to get into that quarry. We did get into the quarry and took a tour of the quarry in the Kentland impact structure in Indiana. And that was really interesting, especially because you could really see the uplifted rocks and the very prominent and impressive shatter cones.
Oh, yeah.
A quarry or a mine?
A quarry.
Okay.
Like a surface open pit quarry that's basically, extracting rock and gravel and things.
Yeah. Okay.
Yeah. Spider Crater, 8 miles, energy 14,710 megatons. And here we go, Texas, Sierra Madera. That's a big one, 8 miles in diameter. Less than 100 million. How much less? I don't know. Maybe since I did this is an old program I did. I'm probably going back 12, 15 years ago, but there's maybe a lot of updated information that could be incorporated into this. But at this point, again, it's not so much the exact specifics, but at least to get kind of a general idea, a general comprehension of it.
I've driven through that one. You
have driven through that, huh?
Yes, and there is mining stuff at the Central Uplift. You can see all the equipment.
Ooh, interesting. I wonder if they could be contacted and we could go in it, because that's what we did. We contacted the quarry owners or maybe we just drove on in and asked them if they would, and they were happy to give us a tour. We all put on our hard hats and down we went.
Yeah, that would be great.
Yeah.
Oh yeah,
they can be contacted. Just don't be trespassing on the property.
Yeah. Okay. Ames, Oklahoma. Look at there, 10 miles in diameter. Some of these, of course, are just terrain modeled because they don't really show up too clearly from the surface. But again, a lot of research is ongoing, and I haven't been able to keep up with the most, up-to-date information on all of this. 10 miles in diameter is now 29,800. So we're close to 30,000 megatons. So now this object here explosion, we're getting, in the range of 3 times the entire nuclear arsenal. Arunga, Chad, this one I've always thought was quite interesting. 10.2 miles, 36,600 megatons. That's 2.4 million Hiroshima bombs going off at once. This astrobleme is part of a multiple impact event. It looks like that there's another right up here. You can see it in the upper right-hand corner. And then above that, there appears to be even a third impact scar. So this could have been an object that was coming in fragmented, probably an early fragmentation, and in the sense that it hadn't had much time for the parts, the 3 objects, if they were in fact that they were originally one object, for them to become separated very far. I've never really known how to pronounce El-Jijit. How would you say this, Kyle?
Yeah, I think you had it right. El-Jijitjin.
Yeah, El-Jijitjin, Russia. Okay. Yeah. So, yeah, getting up there, Gosses Bluff, Australia, 14 miles in diameter. And here you see a central uplift ring, which I think is interesting. And Rees, Germany, 14.4 miles, less than 15 million years old. So that puts it back early Pliocene. I heard a sound. Houghton Astrobleme, Northwest Territories, 7.9 million. We'll just skim through these. Notice you're up to 20 miles here in diameter here. Explosive energy, 200,000 megatons. Now we're getting into a serious global event with the ones that are following. 20 miles. So we're looking, here we go, Shoemaker. Approximately 20 miles, less than 5 million years.
Only 5 million?
Yes.
Wow.
Which is interesting because notice I've mentioned before the Hemphillian extinction that was about 5 million years ago. I was saying that, if you look at the late Pleistocene extinction and then you go back in time to find an equivalent extinction level event, you're back at the Hemphillian, as it's called, and that's usually dated at about 5 million years. Is there a connection? I don't know. Maybe it's just a coincidence, but maybe there is a connection. 17.5 miles, 200,000 megatons. And then we get to Clearwater Lakes. This one's always been fascinating to me. This is like a tandem or a dual impact. Two objects. Are they simultaneous in impact time, or are they separated in time? I don't know the answer to that. I think most of the assumptions are that it was like a twin object that they impacted simultaneous. There may be new studies on it showing that were not exactly simultaneous. I don't know. But notice here, West Crater over here, which has a central uplift ring, is 19.2 miles in diameter, and the Eastern Crater is 13.2. The combined explosive energy, 400,000 megatons.
So that's like the size of the Hiawatha right there, that 19.2 miles.
Yeah. Now, we are now looking at certainly global scale event here. Maybe not enough to cause the kind of mass extinction we saw at the KT or Permian Triassic boundaries, but certainly enough to have global ramifications. Carswell, Saskatchewan, 23.5 miles, over 600,000 megatons. Here's one in Araguaia, Brazil, 25 miles in diameter. Karakul in Tajikistan, again, notice here, 5 million years old. So is it possible we're looking at a bombardment period? 28 miles in diameter. So again, here's two major craters on different sides of the Earth coinciding roughly with a mass extinction level event. Are they connected? I don't know, because I would have to really go in and get a very accurate chronology in order to try to tie these together. But what we're seeing here within the broad parameters, it certainly opens that possibility that we had a period, and they may have not occurred at the same time, but the thing is just, if you have one blow that incapacitates a large section of the planetary biosphere, and before it can fully recover, you have another one or several more. You see, it may not be just one punch that takes it down. It may be several, you see. Siljan, Sweden, 31.2 miles. Look at that explosive energy. Now we're looking at 1,640,000 megatons. Now, again, global event, but very old. Ackerman, Australia, again, very old, but global, 34 miles. You don't have an explosion that unleashes 1,800,000 megatons without having global consequences. Charlevoix, Quebec, 34 miles in diameter. Beaverhead.
Randall,
yes,
you're looking at these ultra large scale asteroids, and you keep saying global consequences. Give us an idea what those global consequences would be for something like this.
Well, you'd have darkening of the skies. You'd probably have intense acid rain. You'd have, large scale regional biomass burning. You'd probably have seismic consequences and perhaps volcanic consequences, because, this is going to, even the Tunguska event caused, detectable changes in Earth's magnetic field that lasted for hours, right? I mean, we're really just at the beginning of understanding how these things are going to affect. But yeah, certainly it's going to affect the Earth's geomagnetic field. It's probably going to strip away the ozone layer, which allows a lot more cosmic radiation to come in, and which could produce mutational episodes. I mean, there's all kinds of things that could happen. Now, obviously, in the immediate vicinity, it's going to wipe everything out. It's going to sterilize that section of the planet. In other areas, the effects will be less severe, but there will certainly be consequences. You can't have, like it says here, a 2,666,000 megaton explosion without there being global consequences.
Are they extinction level events?
Well, okay, now when we're getting up to Manicouagan, look at here. Yes, I think now we're getting at extinction level events. Now, can we correlate? There has been some attempt to correlate Manicouagan, I think, with the Jurassic extinction event, but I think at this point the dating is not strong enough to show a definite correlation. But even without a definite correlation, my thought is that an event like this that could produce a 50-plus mile diameter crater could have effects that would take millennia to play out. I mean, it could cause instabilities in the biosphere, in the lithosphere, in the internal areas of the core. The idea of what happens. We didn't talk about this episode, but we'll talk about it coming up. The possible Yellowstone hotspot being a result of an impact. That by striking the Earth and causing a very deep event, you're releasing the magma from down deep into the lithosphere that is now rising up in a plume to the surface. David Alt has done some work on that. And we'll get into that, especially when we come around to setting up the context for the Great Pacific Northwest mega flood events, which will be coming up. Manicouagan, as you can see, over 7 million megatons. So obviously an event like this is going to destroy everything. Now, an event like this would probably, let's say if it happened in the Western United States, would pretty much wipe out an area the size of the entire Western United States. You'd have fallback debris that, if you had forests, would ignite secondary fires. That's part of it. The amount of dust and soot and stuff injected into the atmosphere is going to be, I mean, we know just from the eruption of Pinatubo that, that amount of dust entered into the atmosphere has global climatic effects. So clearly there would have to be climatic effects, undoubtedly cooling.
Yeah, the cooling, and then of course you'd have crop failure and habitat loss and all of the above. And so people, you could have bottlenecks in many different, if not full extinctions. And
a bottleneck might not show up. See, that's the thing about the late Pleistocene, like particularly amongst humans, because if you may reduce the human population by 90%. But if that other 10% that survives is pretty much genetically diversified, you may not catch a bottleneck, if you're not looking for it. Chesapeake Bay astrobleme, this is 56 miles in diameter. This is the one that created the tektite field that shows up in Georgia. So we're going to wrap this part of it up. Here's of course, the famous, this is again buried under nearly half a kilometer of limestone. But what's under there is this thing, a multi-ring structure with a central uplift. Its estimated explosive energy is 300 million megatons. And of course, this is the extinction level event and impact associated with the rapid disappearance of the dinosaurs at the end of the Cretaceous. And then you have the Sudbury, Ontario, 155 miles in diameter, 340 million megatons. Again, we're talking about a global event. The Vredefort structure in South Africa, 187 miles in diameter. So these are huge events, and thankfully they were a long time ago. But, we might be talking here about a different class of events that Brad mentioned earlier, that if we look at, say, a Tunguska type event. Now, if one of those happened over a densely populated urban area today, you're talking about instantaneously 1 million casualties. Okay, so that would be global event, and certainly in the sense that it would have global economic repercussions. It wouldn't necessarily, if it happened, let's say, over the eastern seaboard, it's not going to have consequences, ecological or climatological consequences too much for, say, somebody in Europe. But if you instantly wipe out an entire city the size of Washington, D.C. or New York, and you kill 1 million people and perhaps leave another 2 or 3 million people really seriously injured, yeah, I mean, that's going to have all kinds of consequences, social and economic. But here's what we're going to get at. And here's what we're going to see, particularly when we come back to talking about the Jungner Dryas and the idea that if you're only limited to crater counting, you may not really be looking at the full broad picture of the kinds of things that would threaten human civilization. Because we are finding that there's evidence for what we could say is multiple simultaneous Tunguska events. In other words, Tunguska was one perhaps piece of a probably spalled off of Comet Encke. Encke was probably spalled off of a much bigger object that might have been 50 to 100 miles in diameter that came into the inner solar system and began this ping pong between Jupiter and the sun. And during that process begins to disintegrate. Now, is it possible that Earth encountered the byproducts of that disintegration more than once? Well, certainly it is, because the Earth crosses that stream twice each year, right? So what we have to begin looking at, and this is what Chandra Wickramasinghe has addressed, Fred Hoyle, Victor Klube, William Napier, William Asher, all of these guys, what they're looking at is the dangers posed by a multiple Tunguska type event, where you might, what if you had a dozen Tunguska objects coming in? Or 100? What would 100? Well, now we're looking at an event that would be on the scale of a thermonuclear war. 100 Tunguskas, my God, that would be, you start contemplating the consequences of that, and they would be profound. Probably not enough to cause a mass extinction event that somebody 100,000 or 1 million years from now could come along and document. But certainly the consequences for the stability of modern civilization would be severely tested. Even maybe to the point where civilization itself would collapse. And see, what these guys are looking at is amassing evidence that makes that a very realistic scenario. See, so it may be that just our crater counting doesn't really give us the full picture, because that is a specific class of objects. You got 100 Tunguskas coming in, and they're exploding in the atmosphere because, let's say, they're between 30 meters and 100 meters in diameter. Well, you're going to have some very serious surface consequences, but you're not going to have craters produced per se. So there we go. And if I have but another minute or two, we are going to jump to, and you can let me know, Brad, when we're out of time. All right, so we'll keep going here. We've seen some of this, so I'm not going to dwell on this. This is Upheaval Dome in Utah, Manicouagan, KT boundary. We've seen all that. Okay, so now we've got the map of confirmed and probable impact structures and astrobleeds. This is really what it looked like a decade and a half ago. We've added to it. Now, again, what I want people to really realize and contemplate is that all of these impacts, virtually all of them are on land. There's a few, yes, we're discovering that there are a few of them on the ocean floor. But again, for every one that you see on land, there should be 3 to 4 that have struck the ocean. So we need to have a more extended conversation about the consequences of oceanic impacts. And we will. And then we get to the Katina or crater chains, which are where you see impacts that would most likely be in the along the lines of Shoemaker-Levy 9, where you have a chain of objects that were originally one object. And they're showing up. We're seeing that there's a lot more of them. And what would cause a crater chain is this kind of event, a phenomena, the string of pearls, Shoemaker-Levy 9, a cometary debris chain. So this was a photograph taken of what had been a single comet nucleus that passed very close to Jupiter Now I'm gonna stop the share screen for just a second. And what we want to understand here is that here's this Jupiter, is this huge, very powerful gravitational mass. And then you've got the sun. And now you've got these objects rotating, this object rotating around. But interestingly, as Jupiter is moving, this object is trailing it. In every loop around the sun, it's zeroing in on Jupiter. So it's honing in on Jupiter, makes a pass. The next pass, it's a little closer. The next pass, it's a little closer. Now, finally, it makes a pass where it's within the Roche limit. The Roche limit is going to be that zone of powerful gravity attraction that is powerful enough that Jupiter's gravity field overcomes the cohesive forces of the singular object, causing it to disintegrate, causing it to fragment, right? That is the Roche limit. So the object is zeroing in on Jupiter. Now, finally, it gets close enough. It passes within the Roche limit. The object fragments. And now as it's coming around Jupiter and moving away from Jupiter, these objects are separating out and they are producing this chain of pearls, as it has been called. So we'll go back to the share screen and pick it up from there. So here we see the string of pearls, and then in July of 2004, the string of pearls, just as predicted, on its next pass, it honed in. So now, like I said, each pass, it's zeroing in on Jupiter. The penultimate pass, it's within the Roche limit, gets fragmented. The next go-around, it comes back, and this time it zeroes right in on Jupiter. And all 21 pieces, which had originally been a single nucleus, now bombard Jupiter over roughly the second week of July 1994. Now, I think, as it turns out, Eugene Shoemaker at the time commented to say something like, well, this is a once in 1,000-year event? Is it once in a lifetime event? Is it a once in a million-year event that we would see this within, let's say, a one generation of being able to implement the technology that allowed us to see it? See, here's the problem. We don't know how frequent events like this are, because we got to have a series of observations that would encompass multiple events, or we get no sense of, did we just get lucky and see a once in a million year event? Or do events like this happen every 10,000 years, every 1,000 years? We don't know. But we are confronted with the possibility that they happen a whole lot more frequently than anybody imagined prior to 1994, because prior to 1994, nobody was imagining anything like this, you see? So now that we've seen something like this, what do we conclude? How do we determine how often this kind of thing happens? Well, we don't know. But if you have something like this and each one of these objects is a Tunguska, see, there is what we might be talking about. And see, if you've got 21 objects like this, and they're all in the Tunguska size range or a little bigger, 21 Tunguskas coming in, or let's say some that's anywhere from 3 to 4 to 5 times as massive, that are still not going to leave craters. But now you're talking about something that's going to be pretty damn significant if it hits the Earth. Now, these objects here, a lot of these are 0.5 kilometer to a kilometer in diameter or even bigger. So obviously, if something like this happened to Earth, boom, we're talking mass extinction level event. We're talking the end of civilization, absolutely no doubt. 21 objects like this would be all she wrote, probably for the human race. Simply because, for one thing, now you've got 21 separate impacts, and just like with the bombing of Dresden or Tokyo, like Dresden, what happens is you have multiple dispersed explosions. What they do is they merge into a firestorm. And this is what would most likely happen in a multiple impact event on Earth, is that the individual fires would merge into a single global firestorm. And so here we see the second generation disintegration of comet Schwarzmann-Wachmann, fragment B, photographed by the Hubble Space Telescope, April 18, 2006. Now you can see from this that the main nucleus is out here ahead, but look what's happening behind it. You've got this fragmentation that could be producing literally thousands of Tunguska-sized objects. Literally thousands. Now, what would happen if Earth encountered something like this? See, these are the kind of scenarios we need to be contemplating. And then, of course, that brings us to this. And the whole idea we've been talking about is that this was the prevalent condition 13, 14, 15,000, say 15,000 years ago. And we have to come up with a way of being explain how we can get rid of a gigantic ice mass like this in a matter of a few thousand years. And when we know that the disappearance of that ice was not a smooth, homogeneous process, but was a series of catastrophic pulses of meltwater reintroduced into the Earth's ocean basins. So that is one of the topics that we're going to certainly be coming back to, and looking at the consequences and in studying the pattern of meltwater associated with the disappearance of the Great Ice Sheet Complex. And that may give us some insight. I will show you one more slide here that will help to convey the situation. This is post Halley, after rendezvous with Comet Halley. We call this a Halley comet, a Halley or Halley type comet nucleus, roughly 10 miles in diameter. And if you do a cross section of it, it's going to be something like this. It's going to be all of this material, much of it going to be bouldery type material, held together in this kind of icy matrix. Can't really call it a dirty snowball because there's too much other stuff in it, but there's certainly a lot of ice. And then also gases that we see out volatilizing, outgassing. So the thing to understand then that we're talking about here is the fragmentation of an object like this, say even 10 miles in diameter, could literally produce a swarm of 1 million objects the size of Tunguska. And see, all of this is information that's come to us in the last, 2-3 decades. And I don't think it's really been incorporated yet into our overall thinking about how are we going to survive as a civilization on this planet for, a few more centuries or even millennia. So in order to address that question, we, of course, have to go to the past. And we have to come up with some kind of chronometer that tells us, well, how often do these kinds of things happen? And now we're also getting models of social evolution that suggest that there are these major interruptions where whole societies collapse in a very short time, which raises, of course, the profound question of what is driving. Is it internal processes? It's something that's sociological, political, something just totally intrinsic to the society itself, or is it something extrinsic? Is it something from outside the society? And most of the ideas for the last half century to century have been intrinsic, that there are conditions within the society that it just essentially loses whatever this forward social evolutionary momentum, and it just fizzles out. But I think we're finding more and more evidence that some of the cultural collapses that are now well documented might be associated with external events, and including perhaps things from space. So we're gonna wrap it up with looking at the final part of this to just give people an idea. We'll go here. We will share screen. And of course, this is not complete by any means, but it'll give people the idea, I think, that this could be a much more critical thing to consider than previously assumed. I call it close encounters. And we can start. I started collecting this stuff. Well, I guess this was 1988. So this is about the time I started collecting this kind of information. This was in 1988. Earth just dodges a big asteroid. This one here was estimated by Bevan French, a scientist with the National Aeronautics and Space Administration, said that if an asteroid this size hit the Earth, the impact would be equivalent to the explosion of 20,000 1-megaton hydrogen bombs. Landing in the ocean could be even more destructive, he said, depending on the depth of the water, angle of entry, and size of speed of the object. It could create huge waves, several hundred meters high. Waves that large could sweep over coastal areas, causing widespread direction. Experts say the Earth's geological record shows evidence of more than 100 large objects hitting the planet. Well, so this is 1988. Now it's almost 200. So it's just about doubled since 1988. The following year, we have a giant asteroid making close pass by the Earth. 1989 PB. Then I'm jumping forward. I'm skipping a lot of years here. And so I'm only showing
a mile wide.
Yeah. It was a close call for planet Earth. Astronomical history was made on May 18th, 1996. Piece of space rock the size of Fayetteville's Cross Creek Mall. So it's only discovered May 14th, just days before the close flyby. We go on here. Studies around year 2000 raises number of dangerous asteroids. Notice the date on this one. 20 years ago today, a study was released. Estimates that there are 900 large asteroids cruising the orbital superhighways where they someday might strike the Earth. Yet so far, astronomers have found only 40% of the big space rocks, each with at least 0.6 miles. Now, of course, one of the things I'm arguing here is that just as important as finding the single big items might be detecting where there might be swarms of much smaller objects, but whose collective consequences could be just as devastating. Maybe much in the way that, you get shot with a .45, you've got one big bullet hitting you, but a shotgun blast could be just as destructive, if not even more so. Then later that same year, another study, asteroid estimates are too low. 9 objects have come close to the Earth since 1991. So that's one a year, right? December of 2000, another asteroid makes a close approach. It's 45 meters wide, 150. So that's the size of the Tunguska object, the Meteor Crater, Arizona object. And here in May of 2001, scientists were rightfully worrying over asteroids. Another one, 2002, huge asteroid narrowly misses Earth. Again, on 2002, large asteroid passes close to Earth. Later, then in a few months later, asteroid buzzes Earth, highlighting cosmic blind spot. June, another asteroid, 2002 MN, gives Earth its closest shaving years. It was traveling over 10 kilometers per second. Coming well inside the moon's orbit. Asteroid pass the size of a football field. So now we're talking something, again, Tunguska class size, maybe even a little bigger. August 2002, near miss asteroid whizzes past Earth, 800 meters wide. Now, 800 meters wide, that's 16 times the diameter of Tunguska. That would have been a real problem if it had hit. So that was August. Then in 2003, October, closest asteroid yet flies past Earth. 24th of February 2004, Earth almost put on impact alert. Again, 2004, asteroid soars past Earth oh so closely. 2004, MN4, a really near miss. Near misses raise rocky questions. Yes, they do, and they ought to. We could keep going here. More studies showing comet strikes surprisingly more likely than anybody had assumed before. Now, has any of this been disproven? No, not at all. January 29, 2008, large asteroid zooms past Earth. 2009, asteroid dodges Earth by near miss. 2015, near miss, giant asteroid 2 miles wide, traveling at 40,000 miles per hour, zooms past Earth. That would suck. Halloween asteroid resembling skull nearly misses Earth. That was 2016, discovered in 2015, TB-145. was the biggest known object to pass so close to the Earth until the year 2027. 2016 will come the closest to Earth on October 31st. On Halloween, that was 2016. 2019, house-sized asteroid zipped by Earth today. Now this is Chelyabinsk size, basically. 2019, city killer asteroid misses Earth and scientists had no idea. It snuck up on us. Scientists stunned by city killer asteroid that just missed Earth. And then asteroid 2000 QW7 won't hit Earth on Saturday, but it could in the future. Asteroid will pass so close to Earth on Saturday that home astronomers will be able to see it. This was September 13th, 2019. To put it, let's see, it's up to 600 meters in diameter. That's 1,800 feet. So again, this is a major event if it hits the Earth. 4 asteroids are buzzing Earth in flybys today. This is 2019. 3 of them were discovered only within the last 24 hours. 2019 TA7, this 111-foot wide asteroid, just made its closest approach to Earth in 115 years. So now we're talking Tunguska class. Again, 2019, spooky Halloween asteroid flyby, one of the closest near misses ever seen. October 31st, 2019. NASA warns 5 asteroids to approach Earth tomorrow. This is January 20th of this year. Biggest asteroid yet to pass close and undetected this year. This is the most recent one just from this month, June 11th, 2020. Within the moon's distance on June 5th. But it wasn't even discovered until June 7th. So in other words, 2 days after it passed within the moon's distance, it was discovered. What I've been getting at for years is that really this is a much bigger issue and demands far more attention than it's been getting. And these days, when all of this stuff is going on, we'll end with this graph right here showing the rate of near-Earth asteroid discoveries. So there's a lot more to learn from this, but I think at this point, maybe we're starting to get the point. The point is simply that we're living on a vulnerable planet. We're seeing a planet now that when we look out into space, we see that there's a hell of a lot more stuff out there in the near-Earth space region than anybody had imagined even a few decades ago. We're also finding out that the history of life on this planet is regularly punctuated by these gigantic catastrophic events. We're also finding out that the entire planetary surface is pockmarked with scars of huge numbers of impacts. We're also discovering that there is evidence that there could be multiple Tunguska-type events. Important point. The objects that the iron objects, like that created the crater in Arizona, relative to lighter density Tunguska-type objects, the lighter density Tunguska objects are far more prevalent, maybe 10 times more. For every one object, then, say that's below 500 or 1,000 feet in diameter, there might be 5 to 10 objects of the Tunguska mass, Tunguska mass and density. So you see what I'm getting at here? There could be a far greater danger of Tunguska type events than anybody has appreciated. And why they're not looking at this, I don't know. But I'm guessing that the B12 Society is probably looking at it. I know a lot of members of the Comet research team are looking at it. I know George Howard is looking at it, who we've had on the show, and realizing, you know what, we really are far more vulnerable. And then the final thing is we're seeing in the evolution of human civilization on Earth is also punctuated by these repeated interruptions. Well, what's causing those? That brings us back to the question of extrinsic or intrinsic forces. A lot of evidence is pointing towards extrinsic forces being the ultimate trigger. Now, something happens from the outside that destabilizes society, yes, then there may be an intrinsic reaction or consequence to that, because it may trigger a destabilization that doesn't immediately drop the hammer on the civilization. It may be a destabilization that takes a generation, 2 or 3 to even recover from, if it does at all, you see? So the problem here is that the vast majority of humans on this planet are oblivious to the bigger world that we're a part of. That's the problem. Mainstream media is not helping, because what we've got here is hardcore evidence, and we're just barely touching upon the surface of this type of evidence. But what's everybody worried about? Look at the stuff people are worrying about. Oh, we're all doomed because of a minuscule increase in carbon dioxide from 300 to 400 parts per million. That ain't much, folks. Is that really going to trigger catastrophic global warming? And that is a very fair question to ask. Now, is there consequences from an increase of 1 molecule of carbon dioxide for every 10,000 molecules of air? Yeah. Is it catastrophic? I think to be skeptical of that is a certainly legitimate stance to take. And when you begin to look at it, you go, there is a downside. But also there's an upside, because a little bit of extra carbon dioxide, as we now know, is fueling plant growth worldwide. It's literally causing a greening of the planet. So, and we're going to talk about that, and we're going to look at some of the evidence and the satellite surveys and stuff that have led to that conclusion. But in either case, my point is that we are neglecting what really could be the most dangerous natural phenomena in our future. And it's a phenomena that encompasses all of the others, because a major impact can have secondary consequences that would mimic every single, like, for example, an earthquake. At this point, an earthquake happens. What can we do about an earthquake, right? Well, an earthquake can be a pretty severe thing, or a volcano going off, right? Or a tsunami, right? We've seen within the last 20 years how we've had 2 devastating tsunamis, right? That were caused by undersea earthquakes. Hurricanes, right? At this point, a hurricane is a natural phenomena, right? And it can cause severe economic disruption. It can take many lives. So you look at hurricanes, tsunamis, earthquakes, volcanoes. Okay, every single one of those can be a byproduct of an impact. Every one of them, see? An impact can cause severe seismic activity around the planet. It can induce volcanic eruptions on a tremendous scale. Obviously, an impact into an ocean. Like we just read, a tsunami wave that could be 100 meters or 200 meters high. What the hell is that going to do when it makes landfall? What's going to happen to Florida? What's going to happen to the East Coast if you had a tsunami 200 feet high coming in making landfall? Right? Well, this is not science fiction. That's the point. You see, there have been a lot of civilizations before us that have risen out of the organic matrix of nature, have existed for a while, and then they've disappeared. Why have they disappeared? Again, it gets to that question, intrinsic or extrinsic. And I think that what we can safely say now is the evidence is pointing us directly towards, in a lot of the cases, extrinsic factors, if not being the death knell for a specific society, at least the trigger mechanism that destabilized them to the point where recovery may have been impossible. You see what I'm getting at here? So if we do not become cognizant of this larger, bigger, this cosmic environment that we are very realistically a part of, I think it's very probable that we could go the way of previous civilizations. If, on the other hand, enough people can say, look, we really do need to look at the big picture. Enough people around the world, if we can get a few million people to watch stuff like this, that can look at the research of the Comet research team, look at the goals of the B612, to listen to Ben Davidson's on the sun. And we're now, of course, seeing that there might be a connection between the influx of this kind of material and the activity of the sun. We're going to address that, right? The sun-grazing comets and the connection between the infall of sun-grazing comets and heliospheric earthquakes, or I'll say sunquakes, coronal mass ejections. There could possibly be, it's looking like now, a correlation, because it's looking like the solar system is functioning as a whole unit, and things don't happen in isolation like we probably have imagined, that something that can affect the entire solar system. And I think that what we're going to be doing is when we come back around, we really begin to look again at the whole, this array of incredible and mysterious phenomena that characterizes the Younger Dryas, that we might have to actually be going, what we're seeing here is the terrestrial manifestation of a solar system-wide event. And it might be very realistic and helpful if we started, for example, looking at the moon or Mars to see if there's anything on either of those two bodies that could actually correlate with the Younger Dryas on Earth.
That's really cool idea.
Decades of research ahead.
Oh yeah, we got some good times ahead of us. But yeah, and I will
Let's
say
dig up the moon.
So, and what make a trip to the moon?
No, we got to dig up the moon.
Yeah,
basically.
we got to dig it up.
Well, we got to dig it up. Yeah,
let's dig it up.
Yeah.
Well, I was thinking if we could come up with some kind of a lasso where we could drag it in within a few miles of the Earth, so it would be easy to access.
Well, a potentially good sign I saw a couple weeks ago, and we were informed about this, and I looked it up and then shared it. But the Space Force, people are recommending and suggesting that planetary defense against these space objects may be part of their larger mission.
Well, see,
and if that's coming about, we need to support that and move those things forward.
Yeah. The other thing I want to know is why do they, when they say we found 90% of the objects or 40% of the, if you haven't found 100% of the objects, how do you know?
Right.
What percentage you found?
Right. Well, you guys know I had the meeting with one of the now commanders of the Space Force headquarters in Denver. And I was invited by him, because I actually met him. He's a fan of ours, believe it or not. He's Matt Lohmeyer. He's now commander at the facility in Denver. He's a fan of ours, and there's actually other members of the Space Force that are fans of ours. So check that out. Hopefully, what'll happen is once he gets settled out there, and he asked me, would I be willing to come and address Space Force about planetary defense? And I said, of course I would. And he was personal aide to General Raymond, who is of the Air Force, who is heading up the program. And so who knows? I mean, maybe within the next few months or 6 months, I can get the opportunity to go out there with General Raymond in attendance and commanders of the bases from all over the country attending and talk about planetary defense. I think that would be very cool. So he specifically emailed me a couple of weeks ago inquiring whether I would be willing to do that. And I said, well, let me check with the guys and see if it's okay with them. So is it okay, guys? If I
yeah, okay. That's cool with us.
Yeah.
But Mike's the guy you got to ask, really.
Right, really. You got to ask Mike.
Who's paying for it? That's all you got to think.
Well, ultimately, I guess if they pay for it, that means you, Mike. I said, just look, fly me out there first class. I'll come. I had that. I've flown.
If they say to meet you at Dobbins Airfield and get into an unmarked black plane, think about it. Okay.
Okay. Well, what I'm hoping is that I cultivate a few contacts in there and I can get some inside information on, what. But, of course, really, I'm afraid that what it's going to come down to is I'm going to have to explain to them what it's all about.
Could be.
And at some point,
a mutual exchange of information.
There you go.
Yeah. Because, people have asked me a lot about that, the whole UFO thing. And, there is I like Paul Devereaux's work. We interviewed. He would be a cool guy to get on the show to interview about his work with the relationship between megalithic structures, standing stones, and the geological substructure of the area in which they are erected, because he's shown that there's a very interesting correlation there. And he has also done work on things, atmospheric effects due to transient changes in the geomagnetic field that may be related to pressures and forces waxing and waning within the crust itself. And some of these can actually produce visible effects in the atmosphere, luminosities and even audible sounds that maybe in the case of luminosities might be, defined or described as a UFO. And then, of course, there is the what I think is the most likely probable explanation for a lot of them is high-performance experimental aircraft testing, and people seeing things that they don't recognize. And of course, that becomes a UFO. The third possibility is, actual aliens from somewhere, which a lot of people, of course, are heavily invested in that belief. But we need to look at that at some point, because I think there's another explanation that has been totally overlooked up to this point. And it's kind of surprising in a way that nobody's considered it. But I think that as we develop the themes and the ideas through these subsequent podcasts, I think we will be coming from different angles, kind of looking at this alternate possibility. And I think that one of the insights, just like so much of the insight that we can now apply to the solution of modern scientific problems, comes from ancient perspectives. When we start talking about mega floods, it can be tremendously helpful to look at ancient accounts of mega floods that are from all over the world, realizing that these aren't just made up things by superstitious pre-scientific illiterates, but are actually stylized ways of preserving these stories about actual events that people lived through, right? But extrapolating from that, we can talk about, there's evidences of stories, all kinds of stories about cataclysmic events in Earth history involving both floods and fires, right? As well as huge earthquakes and upheavals and so forth. And now we're realizing that that geomythic realm is actually perpetuating really valid scientific information, right? Well, if we accept that there is scientific validity to looking at mythology to try to get greater insight to things that our ancient ancestors might have been experiencing, could we apply that to the discussion of, say, gods who are coming from the sky? Because the myths are full of, from all over the world, accounts of gods from the sky. Now, what does that mean? And that's, I think, worthy of looking at. And I think we should come to it, kind of try to strip ourselves of all preconceptions and then take a fresh look at some of those myths. Especially, look at the Sumerian myth. Here we have the myth of global destruction tied directly into an emigration of the Sumerian gods, don't we? What is actually, so the question is there some kind of a real event behind those stories who the actual nature of we may be able to get greater insight into by looking at those stories in detail and maybe without the preconceived ideas? I think possibly yes. So we definitely should come back to that idea at some point, but not until we've laid the groundwork. We're not talking about putting up the rafters until, long after the foundation has been set down. And that's what we're doing now, is we're building a foundation of information and knowledge that I think we can build upon to understand a whole lot of other things: mass extinctions, climate change, the rise and fall of civilizations, maybe accelerated biotic processes, such as we will learn about when we go back to Tunguska, because we see accelerated evolution in the aftermath of the Tunguska event. And then, of course, the idea of what are these stories about the gods of the sky? On the one hand, we maybe is it a metaphor simply for a cosmic event that could be explained purely by naturalistic and non-anthropogenic phenomena? Or is there something more?
All great questions.
Dun, dun,
Yes.
dun.
So, Kyle, if you could do some research and have the answer to those questions for the next episode.
Yeah, I hate to put my hat on there.
We're done.
So good. Didn't want to interrupt.
Man.
Yep.
Yeah.
Yep.
We're done.
Fantastic. Thank you very much.
Yeah.
My
it's an
pleasure,
excellent
boys.
episode.
Extraordinary.
And
Really.
let's mention that we'll soon be having the new website launched within the next week, 2 weeks maybe. And going to be a lot of cool stuff there.
That's right. And there are links in the show notes for websites, for
Have
emails.
quite a few of them.
Yeah, there will be a lot of links. And also one last thing, Crypto Explosion Structures. Best band name ever.
Yeah. A lot of good band names coming out of this podcast.
That's right.
I hope some of those rock and rollers out there are paying attention. Look, hey,
Rockers.
Georgia band Mastodon. Okay, I've often wondered, those guys even know what a Mastodon actually is?
We just entered the 2020s. It's time for a new era of catastrophic rock and roll.
That's
Absolutely.
right. Rock and roll.
Yeah,
All right.
absolutely.
All right. Good night, everyone.
Good night.
Good night.
Great.
Good night.